are going to study a new chapter, waves. We experience waves everywhere in daily life. We speak and hear through sound waves. We see objects using light waves. Okay, and any subatomic particle like electrons, protons, etc. they are also associated with waves. So what is a wave? Wave is a mode of energy transfer. Waves transport energy, and the pattern of disturbance has information that propagates from one point to another. Okay, so wave means the transfer of, it's a mode of energy transfer from one point to another. So the disturbance or energy is being transferred from one point to another, and it appears as waves. All our communication depends on transmission of signals in the form of waves. We know the propagation of radio waves, propagation of microwaves. So these all transfer in from one region to another region in the form of waves. So broadly, waves are classified into three: mechanical waves, electromagnetic waves, and matter waves. So waves are broadly classified into number 1 mechanical waves, number 2 electromagnetic waves, and number 3 matter waves. First one, mechanical waves. Waves which need medium for the propagation are called mechanical waves. For example, water waves, sound waves, etc. they need material medium for the propagation. You are studying the 9th standard, sound need medium for the propagation, isn't it? Using the experiment, we can show that sound need medium for the propagation. So sound waves, water waves, seismic waves, earthquake waves are called seismic waves. All these waves need medium for the propagation. Okay, and such waves are called mechanical waves. Second type is electromagnetic waves. The waves which do not require medium for the propagation are called electromagnetic waves, EM waves. Okay, you will study more about EM waves and what are the different applications and uses of electromagnetic waves in 12th standard. So electromagnetic waves means the waves which do not require medium for the propagation. For example, light waves, radio waves, X-rays, gamma rays, UV rays, infrared rays, etc. So these waves are mainly used for the communication. Okay, and such waves do not require material medium for the propagation. They can travel even through vacuum. And in vacuum, electromagnetic waves travel with velocity of light, that is 3 into 10 raised to 8 meter per second. So the waves which do not require medium for the propagation are called electromagnetic waves. And the third classification is matter waves. Matter waves, otherwise called de Broglie waves. De Broglie waves. This also you will study in detail in 12th standard. What are matter waves and de Broglie waves? Waves which are associated with moving subatomic particles like electrons, protons, neutrons, etc. These subatomic particles in motion produces some type of waves, and these waves are always associated with the moving subatomic particle, and such waves are called matter waves or de Broglie waves. So these are the three different types of waves: mechanical waves, electromagnetic waves, and matter waves. Waves are again classified into two: transverse waves and longitudinal waves. If the particles of the medium vibrate in the direction perpendicular to the direction of propagation of the waves, such waves are called transverse wave. If a wave is propagating along the x direction and the particles are vibrating perpendicular, okay, let wave is propagating along the x direction, particles in the medium vibrate in the y direction, y plane, then such waves are called transverse waves. For example, when we drop a small pebble into a pond of still water, we can see waves are produced. In that wave, if you place a floating material, for example a small piece of cork on the disturbed water, we can see waves are propagating in one direction, but that floating material moves up and down. That means the particles are vibrating up and down, and it is perpendicular to the propagation of the waves. Such waves are called transverse waves. Example for transverse waves are waves along the string, light waves, etc., water waves, etc. Okay. Now, second type of classification is longitudinal waves. If the particles of the medium vibrate in the same direction of propagation of the waves, such waves are called longitudinal waves. Example, sound waves. If sound is propagating in one direction, the particles of the medium also vibrate in the same direction. As a result, compressions and rarefactions are produced. You have studied this in the 9th standard, isn't it? So, if sound waves are propagating, the pressure variation region or density variation regions are also formed in the same direction of propagation of the waves, and such regions are called compressions and rarefactions. Okay, so if the particles of the medium vibrate in the same direction of propagation of the waves, such waves are called longitudinal waves. Example, sound waves. These are the difference between transverse waves and longitudinal waves. Transverse wave consists of crest and trough, and longitudinal waves consist of compressions and rarefaction. Compression is the region of high pressure, and rarefactions are the regions of low pressure. In transverse waves, there are no pressure variations, but in longitudinal waves, there is pressure variation throughout the media. Transverse wave can be propagated through solids and surface of liquid, but not in gases. But in longitudinal waves, they can propagate through solids, liquids as well as gases. Transverse waves, the particles of the medium vibrate at right angles to the direction of wave propagation. But in longitudinal waves, the particles of the medium vibrate parallel to the propagation of the waves. In transverse wave, there is no change in density of the medium, but in longitudinal waves, there is change in density of the medium. Light waves, wave motion along the string, water waves, these are the examples for transverse waves. Sound wave is the best example for longitudinal waves. So we have studied mainly two types of classification of waves. First classification is transverse wave and longitudinal wave, and another classification, waves are classified into mechanical waves, then electromagnetic waves and matter waves. Again, waves are classified into two types, travelling waves and standing waves. Okay, so travelling wave means waves which are travelling from one point to another. For example, sound waves, light waves, UV rays, gamma rays, water waves. These are all travelling its energy, or they are transferring the energy from one point to another. Okay, so such waves are called travelling waves or progressive wave. A travelling or progressive wave can be represented as y equals, this is the equation or this is the displacement of a travelling wave. Y equals A sin kx minus omega t plus phi. Travelling wave travelling along the positive x direction can be represented as y equals A sin kx minus omega t plus phi, where y represents the displacement. As you know, A represents amplitude, then kx minus omega t plus phi is called phase, and here k is called the angular wave number. K is called the angular wave number, and the formula for k is equal to 2 pi by lambda. Okay, that is angular wave number. Then omega is called the angular frequency, and phi is called the initial phase or phase constant or epoch. Okay, so the displacement of a travelling wave travelling along the positive x direction can be represented as y equal to A sin kx minus omega t plus phi, where y represents the displacement, A represents the amplitude, kx minus omega t plus phi is called phase, k is called angular wave number, omega represents the angular frequency, t represents the time, and phi is called initial phase or phase constant or epoch. And here x represents the direction of the wave. If the wave is travelling along the positive x direction, here it is kx minus omega t plus phi. And if the travelling wave is travelling along negative x direction, it is represented as y equals A sin kx plus omega t plus phi. If the wave is travelling along the positive x direction, A sin kx minus omega t plus phi if the wave is traveling along the negative x direction, y equal to A sin kx plus omega t plus phi. Now what is this angular wave number? We have in the wave the distance between two points having the same phase. For example, this is the representation of a wave, and we know these are called crust and these are called trough. These two regions are in same phase and they are called a crust, and these two regions are in same phase, they are called a trough. The distance between two points having the same phase, that means the distance between two consecutive crust or the distance between two consecutive trough, this distance is called the wavelength. That you know, the distance between two consecutive crust or the distance between two consecutive trough is called the wavelength. Angular wave number means 2 pi by lambda, k equals 2 pi by lambda, that is called the angular wave number, and its unit is 2 pi, units radians per wavelength, therefore per meter. So radians per meter is the SI unit of angular wave number. Now second one is angular frequency. Angular frequency, we know omega equal to 2 pi by t or 2 pi nu, nu is called a frequency, and its SI unit is radians per second, 2 pi by t, radians per second. We know a travelling wave travels from one point to another, isn't it? So travelling wave has some velocity. What is the velocity of a travelling wave, or what is the speed of a travelling wave? So if you take omega divided by k, let omega by k, what is omega? Omega is equal to 2 pi nu divided by k, 2 pi divided by lambda. Okay, if you take omega by k, omega is 2 pi nu, k is 2 pi by lambda, 2 pi cancel, it can be written as nu lambda, isn't it? Nu lambda. What is this nu lambda? We know, we have the formula in 10th standard, we have studied the relation frequency nu is equal to velocity of light divided by wavelength. Isn't it? Nu equal to c by lambda. Frequency nu equal to velocity of light divided by wavelength, or frequency nu equal to velocity divided by wavelength. Okay, so what is this nu lambda? Nu lambda represents the velocity. So velocity of a travelling wave or speed of a travelling wave is V is equal to nu lambda, that is equal to omega by k. This is the relation. Okay, for a travelling wave, omega is known, omega is the angular frequency, k is the angular wave number, and omega by k represents the speed of the travelling wave. So travelling wave speed is given by omega divided by k is equal to velocity. Okay children? Now we can derive this formula for speed of a transverse wave on a stretched string. The speed of mechanical wave on a stretched string, it depends on two factors: tension of the string, tension means force, and linear mass density. Linear mass density means mass divided by length. Mass of the string divided by its length is called linear mass density. It is represented by mu. Okay, so experimentally we can say that the velocity of transverse wave on a stretched string, it depends on what are the two terms, tension and the linear mass density mu. So we can derive the relation between velocity, tension and the linear mass density using dimensional method. Okay, so we can write velocity depends on two factors, tension and linear mass density. We can write velocity is directly proportional to T raised to A, mu raised to B. This is the method of deriving the relation using dimensional analysis. That is the second application of dimensional analysis. Already you have studied in the first chapter. So velocity is directly proportional to T raised to A, tension raised to A and mu raised to B. Or velocity V is equal to a constant K into tension raised to A, linear mass density raised to B. Now we can find out the values of A and B. Applying the dimensions. Velocity means Lt raised to minus 1, K is a constant, no dimension. Tension means force, mLt raised to minus 2, the whole raised to A. Then mu means mass per unit length, mass divided by length. So mL raised to minus 1. Okay, mass divided by length means ml raised to minus 1 raised to b. Now, we can take the m terms together, m raised to a plus b, l raised to a, here minus b, t raised to minus 2c, isn't it? M raised to here a, m raised to b, m raised to a plus b, l raised to a, here minus b, t raised to minus 2a, sorry 2a, t raised to minus 2a. Left side no change, lt raised to minus 1. Then equating the powers of length, equating the powers, first mass, here a plus b, here there is no mass term in the left side, so a plus b equal to 0. Equating the powers of length, here 1 equal to here a minus b. Then equating the power of time, here minus 1 equal to here minus 2a. So what is the value of a? A is equal to 1 by 2. Now substitute in this relation, we have a plus b is equal to 0, a is 1 by 2, isn't it? So b is equal to minus 1 by 2. A is equal to 1 by 2 and b is equal to minus 1 by 2. Substitute the values in the first equation, we have therefore v equal to k t raised to a, t raised to 1 by 2, mu raised to b, mu raised to minus 1 by 2. Okay, so the relation is velocity v is equal to root of t divided by mu. Experimentally k equal to 1. So the relation between velocity, tension and linear mass density is v equal to root of t by mu. So we can derive the relation using dimensional method. So velocity of a transverse wave on a stretched string is v equal to root of t by mu, where t represents a tension and mu represents linear mass density. Okay. Now we can do some numericals. The steel wire of 0.72 meter long has mass of 5 into 10 raised to minus 3 kilogram. If the wire is under a tension of 60 Newton, find the speed of transverse waves on the wire. So mass is given, mass is equal to 5 into 10 raised to minus 3 kilogram. Then length is given 0.72 meter, then tension is also given as 60 Newton. We know the velocity of transverse wave on a stretched wire is v equal to root of t divided by mu. Isn't it? Velocity v equal to root of t by mu. T is known. What is mu? Mu is linear mass density, which is given by mass divided by length. Here mass is 5 into 10 raised to minus 3 divided by length is 0.72. And if you simplify, the answer is 6.9 into 10 raised to minus 3 kilogram per meter. Mass by length, so kilogram per meter. So this is called a linear mass density. Directly we can substitute. Direct relation, 60 divided by 6.9 into 10 raised to minus 3, and if you simplify, the velocity is found to be 93 meter per second. So velocity of transverse wave on a stretched string is, we have the relation v equal to root of t by mu, and after simplification the answer is 93 meter per second. Another one, a wave travelling along a stretched string is described by y equal to 0.005 sine 80x minus 3t meter. Okay, all the values, all the variables are in SI unit. Calculate the amplitude, wavelength, period and frequency of the wave. So we know displacement of a travelling wave is given by y equals a sine kx minus omega t plus phi. This is a general relation, isn't it? So displacement of a travelling wave is y equal to a sine kx minus omega t plus phi, and here phi in the relation, given relation, phi is equal to 0. So here if you compare the two relation, what is the amplitude? Y amplitude A equals 0.005. So we got the relation of amplitude as 0.005 meter. So that is the first part. Second one, we have to find out the wavelength. We have, if you compare, k is equal to 80, no? Kx minus omega t. Here k is equal to 80. angular wave number k is equal to 80, and we know angular wave number k is equal to 2 pi by lambda. So 2 pi by lambda is equal to 80, or we can write lambda is equal to 2 pi by k, that is 2 into 3.14 divided by k is equal to 80. Okay. And after simplification, you will get the answer as 7.85 into 10 raised to minus 2 meter. Just compare the relation, the general form and the given relation. K is equal to 80, here k is equal to 2 pi by lambda. Substituting and simplify, you will get the lambda as 7.85 into 10 raised to minus 2. Now, third one, we have to find out the period, time period. Here we know omega. What is that omega here? In the given equation, omega equal to 3, isn't it? So omega, we have omega is equal to 3. Omega is equal to 2 pi by t, no? The relation angular frequency omega equal to 2 pi by t. Directly we can write t is equal to 2 pi by omega, or 2 into 3.14 divided by omega is 3. And after simplification, you will get the answer of time period as 2.09 seconds. Clear? Then last one, frequency. Fourth one, we have to find out frequency also, frequency nu. If time period is 2.09 second, what is the frequency? We have frequency nu equal to 1 by t. The direct relation, frequency nu is equal to 1 by t, or nu equal to 1 by time period is 2.09 second, and hence the answer is 0.48 hertz. Okay, so frequency is equal to 0.48 hertz. So using the direct relation, we can just compare the two relation, and we can find out the wave number, we can find out the wavelength, then angular frequency, time period, frequency, etc. Okay.